Hello and welcome to Resonance in RLC Circuits. This video was created for ECE 4823B, that's Numerical Methods in Electrical Engineering at the Georgia Institute of Technology, and was designed for use as supplemental material in ECE 2040 or any other linear circuits class that discusses resonance. So I guess the first thing we'll want to do here is define resonance. Resonance is a vibration of large amplitude in a mechanical or electrical system caused by a relatively small periodic stimulus of the same or nearly the same period as the natural vibration period of the system. And that sounds like a lot of words, but we will dive into what that actually is. So for this example, we're going to be discussing series RLC circuits only. So this is what a series RLC circuit looks like. As you may have guessed, it is a resistor, a capacitor, and an inductor in series with a voltage source. So in order to achieve resonance in one of these circuits, the values of the inductor and the capacitor need to satisfy this equation. This is the equation for the impedances of both of these, and they should sum to 0 in order for them to cancel out fully to achieve resonance. So what we're going to be interested in looking at in this study of the RLC circuit is the voltage across the capacitor at a given time, the equation for which is given here. Now I'll assume you've seen this equation before, and suffice to say that the source voltage, Vs of t, is going to play a big part in determining the response. So since it's going to play such a big part, we should figure out what this Vs of t could be. It could be 0, a ramp function, a step function, or a sinusoid. It could be other things, but we're just going to look at those for this video. So first, let's look at what happens when the source voltage is 0. And what happens when it is 0 is that if we don't have an initial condition on our capacitor, then we're going to get an absolutely trivial solution. And if you don't believe me, then here's a simulation. As you can see, nothing is happening because there's nothing to excite the circuit, and there's no initial condition to do anything with. So we're going to use an initial condition that the capacitor is initially charged at 1 volt for the rest of these simulations. So now there's a few little definitions that we need to make before we go into the rest of this. So the first is the attenuation factor, which is the measure of how quickly the transient response will return to its steady state value. The second is the resonant frequency, or the natural resonant frequency, which is the frequency that the circuit will resonate at if driven by a source. And the third is the damped resonant frequency, which is the frequency that it will resonate at when not driven by a source. The last one here is the damping coefficient, which is another measure of how quickly the oscillations disappear, but the range of values that this number can take is easier to understand than that of the attenuation factor. Why do I say that? Well, if this number that we're going to call zeta is greater than 1, then this circuit is overdamped. If it's equal to 1, it's critically damped. If it's less than 1, it's underdamped. And if it's equal to 0, then it's undamped. And we'll go into examples of those to show what they are. And the first example that we're going to do is this overdamped case. Now you can see all the values of the components there, but the important thing is that our zeta is greater than 1. So as you can see what's happening here, the source voltage is again at 0 because we decided that. So the capacitor voltage here is slowly decreasing because the resistor is taking up so much energy out of the circuit that it doesn't let the capacitor voltage change as rapidly as it would like to. So now we'll go into the critically damped case, and all critically damped means is that the values of the components are chosen in such a way that the voltage will be able to change as rapidly as possible without going into oscillations, as we'll see in a minute. So as we can see with the simulation, the capacitor voltage dropped much more quickly than previously because the resistor is smaller and will let it, and now it's staying at 0 because the source voltage is at 0, so there's nothing to drive the circuit. So now we'll look at our underdamped case, and here zeta is well below 1, so we'll expect oscillations, and our damped resonant frequency is at about 10 kilohertz, so let's see what happens. And as we can see from the simulation here, it's oscillating as we expected it to, and it's decreasing in amplitude while it's oscillating. So that's because the resistance is small enough to where it will allow for oscillations, but not so small to where it will oscillate indefinitely. It's going to return to steady state eventually. So now we'll look at this undamped case where the resistance is 0 and zeta is 0, so now we should expect oscillations to just keep going. So we get to the simulation, and just as before we have oscillations, but also just as we expected, the oscillations are staying between 1 and -1. It's undamped. There's no resistance to take any energy out of the system, so it just keeps on oscillating back and forth. So now let's do something fun. Let's do 5 different damping coefficients in real time at the same time, just so we can see the real-time responses and compare them to one another. So we see this simulation here. There's 5 different colors for these Vc of t's, and these 5 colors match up to the colored boxes in the previous slide. The magenta and the green are the overdamped, the black is critically damped, and the red and blue are underdamped. And we're getting pretty much the results that we were expecting, and also they're all converging back to steady state at 0. So now let's move on to where our source voltage is a ramp function. And the same damping conditions apply as previously. We're just going to be looking at a new source voltage to see what kind of response that gives us. So first we'll look at our overdamped case with the same component values as were in the previous example. So we take a look at the simulation here, and we note that the capacitor voltage is having a lot of trouble keeping up with the source voltage, and that's again because the resistor is taking a lot of energy out of the circuit. It eventually gets there, but slowly because of the high valued resistor. So now we'll take a look at the critically damped case, and just as before, we would expect the capacitor voltage to rise as quickly as it can without going into oscillation. And as we look at the simulation, it's doing just that. It was a little bit slow at the beginning, and it's a little more rounded at the top than the source voltage, but it's got the same shape. It's maintaining the same steady state at the end. So now we get to our underdamped case, and just as before, we're going to expect some oscillations to occur because our damping coefficient is so low. So, as we see in the simulation, we are getting oscillations, which is good because that's what we expected. We're getting oscillations both on the upward sloping part of the ramp and on the flat part of the ramp. And again, the oscillations are occurring because the resistance is too low to take out enough energy to make them stop. And just as before, let's take a look at this 5 different damping coefficients going on at the same time so we can compare them to one another. So as we see, we've got the same colors representing the same level of damping coefficients. Blue and red are still underdamped, green and magenta are still overdamped, and black is still critically damped. So we're getting the same results from what we expected and what we saw previously, with the underdamped oscillating the overdamped, taking a while to get up there, but we note that they're all converging to that 3 volts. And now we'll take a look at what happens when the input voltage is a step function. And we'll now take a look at the overdamped case and note that the damping conditions have not changed. So the voltage is at 0 right now, there's nothing particularly thrilling to look at. But as it jumps up, you'll note that the capacitor voltage is a little bit slow to follow, and as when it jumps back down, due to the overdamping. It's the same thing we expected and we saw earlier, being slow to respond. We will now jump to our critically damped case. And again, it's at 0 right now, so we'll just have to wait a moment for it to jump up. And there it goes. So again, the critically damped case is the case where we expect it to follow the source voltage as quickly as possible without going into oscillations, and you'll see that we're getting no oscillations, so that's good. We will now move on to our underdamped case where we expect oscillations. So we're at 0, and when it jumps up, we should see there are the oscillations that we were expecting because the resistor is not taking as much energy out of the circuit as it needs to in order to prevent them, so we see them both on the up and the down. Now we'll continue our journey into 5 different damping coefficients at once for real-time comparison. So we should already know what to expect by the time the source voltage hits 1, and as we expect, the blue and red underdamped cases are oscillating, the green and magenta overdamped cases are slower to respond, and the black critically damped case is again rising as fast as it can without oscillating. So now let's go to the final example when our voltage is a sinusoid. And I'd like to go back to the resonant frequency real quick, this 1 over the square root of LC, because this is really going to govern the response. So as you see, we have the circuit set up to resonate at 14,142 radians per second. So this is a numerically simulated Bode plot of the system, and as you can see, there's a peak around 14,000 radians per second, which is what we expected. So we'll see a little bit more of the time domain amplitudes at some of the frequencies in this Bode plot here in a moment. The first frequency that we should look at is the resonant frequency. That should be the highest, that should resonate. So let's see what happens in the time domain. So we look at the time domain and we see that the voltage source is adding energy to the system, and it's adding energy to the system at exactly the right time, at exactly the right frequency, to where it's tugging the capacitor voltage along. Note the capacitor voltage is about 7 or 8, the input voltage is about 1. That's the resonance, that's the increase. So now let's take a look at an 11,000 radians per second sinusoid and see what the time domain looks like on that. Now in theory it should display some resonance, but not quite as much as at the resonant frequency. So when we look at the time domain, we notice that it's sort of starting to resonate. You know, we're keeping going, but then it starts to die down a little bit because it's not adding energy at the correct time, it's even starting to subtract some energy. And note that it maxes out at about 4 volts, whereas earlier it was 7 or 8. So now let's take a look at a sinusoid at 20,000 radians per second, which is a little bit further away from the resonant frequencies. So it should still display some resonance, but not quite as much. And as we look at the simulation run, that's exactly what's going on. It's starting to build up again, just like the other ones, but then it dies down. it's maybe maxing out at 2 or 2.5 volts here. So I mean, as we see, the further away we get from the resonant frequency, the smaller the amplitude gets. So now, just for completeness, we should like to take a look at a 50,000 radians per second signal, which is quite far away from the resonant frequency, just to see what that amplitude looks like. It should really not resonate at all. And as we look at the simulation, we find that that thought process is correct. It's not resonating. The frequency of the input voltage is such that it's trying to get it to resonate at the wrong frequency. So it's just going to keep bouncing around at a very low amplitude and not really get anywhere. So I'd like to allocate the last part of this video to the discussion about natural resonant frequency versus damped resonant frequency. I haven't really gone too much into that. I've sort of done them both separately, but I'd like to show an example where both of them come into play. So in this example, I'm just going to excite a series RLC circuit tuned to 10,000 radians per second. And then once that builds up, I'm going to take away the voltage source so it has a chance to resonate at omega 0 and omega d, just to show the difference there. So we start the simulation, and it's starting to resonate at omega 0 because that's the resonant frequency. So then all of a sudden the voltage source goes to 0, so at this point it's going to resonate at omega d. And I know that's a little bit hard to see because the frequencies are so similar, but that is what it's doing. And I'm just going to continue talking through all these credits because there's not a whole lot else to say. I'd like to thank you guys for watching this video, and I hope it was informative and that you learned something from it.